All right. This is one of, as a student, this would be one of my favorite types of exercises because it's an exercise that we've done already. Basically, we've done all of the work already. We just need to refer to past stuff. So let's see here. So we want an increasing function f to be integrable on AB. So let's see here. F is bounded because if you take the infimum, the infimum over all AB of f, so this would be the infimum over all values of x in AB of f of x. Well, this is an increasing function, so the infimum is going to be f of a. And that's going to be a real number because f maps into R. And similarly, if you take the supremum, then that has to be f of b, which again is in R. So f never maps to, or the infimum of f is not negative infinity and the supremum is not positive infinity, and so it's bounded. All right. All right. So now here's the part that we've done before. By exercise 3-12, B equals the set of all x such that f is discontinuous at x has measure 0. And this I remember being more of a difficult exercise. Well, maybe not difficult, but it took more time to do. So this is where all the real work of this exercise is. It's in proving that the set of discontinuities of f has measure 0. But we already did that. We did that in the last section. Well, the exercise set for the last section. All right. Then, by theorem 3-8, what does that say? It says that if you have a function which is bounded, then this function is integrable if and only if its set of discontinuities has measure 0. So by theorem 3-8, the fact that the set of discontinuities of f which is b, has measure 0 means that f is integrable. So we're done. Now, of course, to actually prove that the set of discontinuities has measure 0, you need to do some sort of argument. I think this can actually get a little complicated. You can prove that the only type of discontinuity is a jump discontinuity, because if you approach, if you take any x value between a and b, the limits of f from the left and right have to exist, because you've either got an increasing set with an upper bound or a decreasing set with a lower bound, and those always converge. So that means that the only type of discontinuity you can have is a jump discontinuity, and then you can only have countably many jump discontinuities, because if you have uncountably many jump discontinuities, then f of b needs to be unbounded. That's the basic idea. I think that's generally how I solved exercise 3-12, but you can go back and see for yourself how I did it. And yeah, this is a nice quick exercise if you've done 3-12 already. If you haven't, then you need to basically do that entire exercise here. And so this is like sort of the type of thing where I would get this if I were taking a class, and I'd be like, oh, yeah, it's just an obvious consequence of this other exercise. And so, of course, as a joke, like I'd go up to my professor and I'd be like, hey, can I just cite this other exercise that I didn't have to do for this class and just use that to prove this result. And they're like, no, you have to actually do the work, because that's the whole point of taking a class, is learning. But still, it's still nice when you can sort of like get to a problem and go through it because you've already done it already and you feel more accomplished, and it can be kind of refreshing. So it's nice to have that every once in a while when you're working through problems and thinking about them. But anyways, yeah, really short solution. We've done all the work, and so we're done.